case, we're just going to say, spatial database directory tractions.spatialdb. So let's look at some examples. There are 5 examples that use friction within the 3D hex 8. And step 10 is static friction, where we don't exceed the threshold for slip, so it's not quite that interesting in terms of what the solution looks like. We're going to run step 11, which is static friction, and there is slip, and it's a static simulation. Then 12, 13, and 14, we're going to run step 14. So step 12 is a quasi-static, where we're going to load the fault gradually with constant velocity boundary conditions, and then the fault will fail, and we'll continue to apply those velocity boundary conditions. And so in the static friction, once it fails, it just begins to creep along at a steady state slip rate. In step 13, we're going to use slip weakening with stick slip behavior. And in step 14, it's rate and state with stick slip behavior. So let's look at step 11. So I'm going to bring up let's bring up Emacs. So here we are, we're at step 11. And so let's look at what we have here. We have, this is going to be a static simulation. So we have a total time of 0 seconds. Because we have slip rates in our fault constitutive model, we need a realistic time step so that they are non-dimensionalized appropriately. So we're going to, because we're in sort of the static, quasi-static type regime, we're going to use a time step of 5 years so that we have correct non-dimensionalization. We're going to put our boundary conditions. We're going to use X positive, X negative, and Z negative. These are the same 3 boundaries that we've been using for a number of our 3D hex 8 examples. We're going to have a single fault interface. We'll output over the domain and subdomain. Again, for our subdomain, we're going to get output on that. We use the output solution subset component. We're going to use the nonlinear solver because we're using a quasi-static simulation with friction. Here are our boundary conditions. So with our static problem, what we're going to do is we're going to put some compression on the fault. So we'll put a -1 on the X positive face here. That's our node set from Qubit, where we constrain X and Y degrees of freedom. We're going to give it 1 meter of axial compression and 3 meters of lateral displacement. On the X negative face, that's this component here, constrain the same degrees of freedom, and we'll give them the opposite sense of motion. So again, we're going to have compression in the X direction and then shear in the Y direction. On the bottom face, we're going to use our roller boundary condition, so 0 displacement in the Z degree of freedom. Here's our fault, and this is exactly what we essentially had in our in the slide where we set our fault to be a fault cohesive dynamic object. We give it the node set from Qubit fault. We set our friction equal to static friction. We again have to set our quadrature scheme for the fault. So we're using hex cells. So we're in the Fiat Lagrange in cell dimension 2 for the fault because we have quadrilateral cells on our fault for a hexahedral mesh in our domain. Our friction properties are going to use the spatial database, static friction, and in this case, I'm not using any initial tractions applied directly to the fault. Here are my PETSI parameters. So here's my friction sensitivity solve. Sorry, grab the window rather than the. And so I'm told a max iteration of 25. You want to make sure, if you're doing a friction simulation, especially with a large fault, that you don't is that your linear solve for this update of your slip relative to for a given perturbation in your tractions converges, because if that doesn't converge, then you're definitely not going to converge for your friction model, or for your nonlinear solve. And so you want to, generally what we do is we keep this friction KSP converge region equal to true. So that tells me whether I have enough maximum iterations set here. And so in this case, we're going to use VTK output. And so basically, as in most of our other examples, we're just giving the file names for the VTK output. Obviously, for the ground surface, we again have to tell it for our output solution subset which part of the ground surface we want. And so that's it for the parameters. Are there any questions on the .cfg file for our friction example here? It looks like we have a question coming up.
Yeah, it looks like Aaron is typing.
Okay, so when I run the example, I'll show you where in the output file we see the results of having in that converged region equals true. So whoops. Okay, so I'll stop sharing my window there, and I'll switch my terminal. We can run it. It's no reason to be skippy on the screen. Bump it up even more. So we're going to run step 11. So pilot step 11.cfg. And I'm going to capture it to a log. So I'm just going to capture it to a log like this. And so that it's running, so it ran. So let's look at the output. Whoops. Let's look at the log file. So it has our usual reading all the information in, tells how many node sets we read in. There's our quadrature information. So let's scroll down. We get some. So this is all the same stuff that we see. We're initializing. So here we see solving equations. Then we see these two linear solve converge due to absolute tolerance iteration 0. So this is our friction KSP converged region equals true. Then what we see is we're going through the SNES. So here's our main solve where we have SNES, and then you see an indentation, and then the KSP. So this is our nonlinear solver is going to iterate, and at each iteration it calls a linear solver. And you'll notice that the nonlinear solver residual is different than our linear solver residual, and that's because this is not a true residual, but a preconditioned residual. So you'll notice they're similar, but they're not exactly the same. And so don't worry about that. You can actually, there is a specific solver setting that you can get the true residual if you want to see the true residual. But you notice that here in our linear solve, we went down, we converged at 10 to the minus 12. It told us that our linear solver, that's KSP converged region, it converged due to relative tolerance. Then it said, so in this case, we actually converged due to our linear solid relative tolerance earlier than what we really, so normally we'd want this to be an absolute tolerance. And so we'll have to look and see, we may have to adjust parameters there, but it's still a very small value, and so we may be able to get away with it. In this case, our linear friction model to our friction solver converged due to absolute tolerance in 9 iterations. So it doesn't, and our line search, it's telling us what it's doing when it's doing the line search for the nonlinear solver. We then go back to the friction solve, get its update, no updates. Now we're in the 2nd iteration. We've now reduced our residual. We're at 2 times 10 to the minus 2, I believe. Now we're down to 1 times 10 to the minus 3. And so now we're going to do another linear solve. Now we're going down to 10 to the minus 14. Do another update. 4th iteration of SNES. Now we're at 10 to the minus 4. 5th iteration, 2 to the minus 4. 6, 2 to the minus 4. 1 to the minus 4. This is a through-going fault, so that's why it's going to take longer. So we have 8, 9, 10, 10 to the minus 5. I think it's going to take around 30 iterations. Maybe a little more. 32, 33, 35. Now we're at 10 to the minus 8. 40, 44. 47, 48, 49, 50, whoops. Oh, it did converge. Just in the nick of time. 51, and went down to 10 to the minus 9 times 10 to the minus 10. Here it told us the nonlinear solve converged due to the F norm absolute. So it hit it was not a relative tolerance, it actually hit the absolute tolerance. And you notice here those inner friction values were, converging to absolute tolerance in 5 iterations. A really great way to, when you dump things to your log file, a great way to look and see if things converge is you just do a grep or nonlinear on my log file. And I can pull out, if there was multiple time steps, I'd pull out, what this looked like for multiple time steps, and I could see, just what that one line looked like to make sure there was never any divergence. I can also do a grep for, I think I'm just grep for div. There's no div, so no diverged warnings. So that's what we see when we run the problem. Now let's look at the results. So we'll switch into pair view. So let's load up the ground surface and the fault. And let's do the fault info as well. So first, let's look at the fault info. In the fault info, we only have the normal direction. So that's not very useful. So let's not even look at that. So now here we have slip and traction. So let's look at slip. Let's look at traction, actually. Let's look at the shear traction, so traction in the x direction. So there's my traction in the x direction on the ground surface. Let's look at displacement. And so let's deform the ground surface, say a factor of 200. So this is a static. Remember, I did a static simulation. So there's, we squeezed everything. So let's go in and let's plot our displacement vectors. So there you can see our original configuration. We sheared everything, and then we did a little bit of compression to give us some fault normal tractions. Here's what our change in the, or here's what our fault tractions actually look like. So put a displacement bar on there. So we don't see what our initial tractions are. We only see what our final tractions are because of the static problem. So they're on the order about 1 times 10 to the 7. If I change to tractions in the Z, so this is our compression. Notice that the compression on the center of the faults is different than it is off to the sides. Because we're coming out here to the sort of the free surface on the lateral edges, we tend to have lower tractions out there. And so our Y tractions, notice our Y tractions are much, much less than our X tractions and Z tractions. So these aren't X, Y, and Z. These are Z is the normal traction, X is the shear traction, horizontal shear traction. So there's what we have for our faults. Our static simulation isn't nearly as interesting as our dynamic simulations or even our quasi-static. Are there any questions on this very simple static problem? Okay, let's make things a little more fun. So I'll delete this. Oops. We'll delete these and then we'll exit out of pair view here. So let's go back and look at our input files for step 14. So now we're going to do rate and state friction in step 14. And so first we look here, use all the defaults from before. We essentially using now our total time. The only difference here from that last step 11 is our total time now is 300 years. We're going to use a time step of 2 years. And now we're going to have we're doing a slightly more sophisticated boundary condition in that we're going to give it an initial value. We're going to put in the compression as a static displacement of -2 meters on the positive X face, but then we're going to give it a rate for the Y direction. So we're going to give it 1 centimeter per year in the Y direction, in the plus Y direction for the X positive face. On the X negative face, we're not going to do any initial displacement. So that's here. We're just going to do a 0 displacement, but then we're going to do -1 in the other direction. So thinking about this, we're going to, on our X positive, we're going to put a static displacement. Before we did 1 meter on both the X positive and X negative faces. This time we're going to have, on the X negative face, we're going to have a 0 initial axial compression, but then on the plus X face, we're going to go 2 meters rather than just a meter on each end. We're going to do all the displacement on the X positive face, but then our shearing will be evenly split with -1 centimeter per year on the plus Y face and -1 centimeter per year on the minus Y face. And again, roller boundary conditions on the Z negative. Our fault parameters here, we have a fault cohesive dynamic object for our spontaneous rupture. Now we've explicitly added in our 0 tolerance. We're going to use 10 to the -11. We're going to put in our linear slip rate for our transition between sort of our linear dependence on slip rate and the logarithmic dependence at 10 to the -9. So just a couple orders of magnitude greater than our 0 tolerance. Then we put in our quadrature information. Now we have a number of parameters for our fault constitutive model. So here's what they look like in just sort of our comments. So our coefficient, reference coefficient of friction of 0.4, reference slip rate of 10 to the minus 11, characteristic slip distance of 5 centimeters, A of 0.002, B of 0.08, a cohesion of 0 pascals. So here's what that looks like when you put it in a uniform database. For our state variable, this is our friction state variable. We're going to give an initial value to that state variable. Then we're going to give it a value of 2.5 times 10 to the 9th seconds. And this is how we just came up with 2.5. We're going to use a steady state variable that comes from the characteristic slip distance divided by the reference slip rate. And we're going to use here's our solver parameters. So we use, I think these are the same parameters that we used in our last example. But now with rate and state friction, we're going to tighten up our tolerances a bit. Because we tend to have these very low slip rates in our rate and state friction. So our relative tolerance is now 10 to the minus 16, absolute tolerance of 10 to the minus 12. And I'm going to force this right here. Let's go right away to relative tolerances of 10 to the minus 20. Absolute tolerance of 10 to the minus 12. Remember, our zero tolerance up here was 10 to the minus 11. So our fault, we want that to be, we're going 1 order of magnitude smaller for our linear solver tolerance and 1 magnitude larger for our nonlinear solver tolerance. We're going to give it plenty of iterations because our through-going fault takes a lot longer to converge than what it would if we had it confined to the middle part of our domain. And then we have our output. So we're going to output over the domain every 20 years. Remember, we have a 5-year time step for our simulation. Our ground surface, we're going to output every time step. That means that's what the skip equals 0. As well as our faults, we'll output every time step. So skip equals 0. We'll do 20 years for our state for our sort of stress and strain. And so that's it for our input file for our quasi-static simulation with rate and state friction. So it has just the time dependence of our loading as well as the rate and state friction parameters. Any questions about setting up this type of simulation? Okay, let's run it. Oops. Step 14, right? Step 14, yes. So I sent it to a log, and then I'm going to look at what the log is. Oops. I want to update the log as it's running. See what's going on. So we see a lot going on. It's the solver is cranking away. It looks like it goes a lot faster on my screen than what Adobe Connect can update. It's 38 iterations goes up to 50. And so what we'll see is that this is a quasi-static simulation, so the fault isn't going to start slipping right away. And so it won't need any nonlinear iterations for several time steps. Then when it starts to slip, you get that with that stick-slip behavior, then it'll take a bunch of iterations. And then once the fault sticks again, then it'll be back to just using one iteration.
Yeah. You see Aaron's question here about the tolerances?
Yeah, so the tolerance are telling the solver how low the residuals need to converge. Yes. And so let's look at step 14 in the log. So let's do a grep for first. Let's I'm going to do a grep for nonlinear in step 14.log. And so what it did is it pulled out all of those times where it said whether it converged or not and why. And so you'll see here that for every single time step, we now have what happened, what the nonlinear solver decided to do. And so you'll see for a number of time steps, it converged to the absolute tolerance in one iteration. Then as the fault started to slip, it took 2 iterations. And so what this is just a small piece of the fault started to slip. And then as it started to slip more and more, and that nucleation region actually got bigger, it started to take a few more iterations. And then now we're starting to get slip over most of the faults. So it went to 12, 11, and then here we're at 44, 65. And so there are a few time steps where the fault was slipping, and then it locked back up again. And so when the entire fault locked back up, then we're back down to 1 iteration, because when we solved our linear system, the Lagrange multipliers were consistent with our fault constitutive model. And so now we're back to 1 iteration for a bunch of time steps. Now we're getting some more stick-slip behavior, so we get the thing nucleating again. That one takes 10, and we're back to 4. Then we're back to sort of most of the fault slipping. Then just a little piece of the fault is slipping, and then we lock back up again. And then we can also look at see what our linear solve is doing. And you'll see, so most of our linear solves were taking an error of about 26. They were converging to the absolute tolerance because we really pushed our relative tolerances down. And so we see everything looks good. And so you'll see a lot of these that are our friction convergence. It was basically converging in 10 iterations. Most of our linear solves for the whole main system were 28. There's some 30s. Depends on where it is and how close it is to conversion and nonlinear solve. And after the end of this example, I'm going to go in and we're going to mess around with some of our solver tolerances and try and debug if things go wrong. So we ran it. We verified that all of our nonlinear solves converge. So let's look at the results. So we're going to look in pair view. So let's load up step 14. We'll look at the faults. So in pair view, when you have a bunch of VTK files with timestamps, if you want to look at the time histories, it's collapsed. So if you open up, we want to open up the one, instead of open up like the first file, we want to look at all the time histories. So we open up them as a group. So the fault and the ground surface. So there's our fault, there's the ground surface. Let's magnify things by a factor of 100. So let's do 200. Let's show our displacement vectors on our original. So we'll do increase here, we'll scale them. We did a factor of 200, so let's have them point from the original. So there's our original displacement. Let's show the wireframe. Whoops, our wireframe. I want my ground surface wireframe. Sorry, this ground surface is a wireframe displacements. So there you can see, as we squeeze things in, this is a 3D problem. We got a little bit of uplift. The left-hand side was fixed in the X and Y, so that's why it didn't move. And then down there on the fault, let's look at I need to select the fault. Let's look at slip. So we have 0 slip here. Let's go to the very end. Here we see an offset in the faults. We need to get what our slip scale looks like. Everything is almost uniform, so we need to recalibrate what our slip scale looks like. So here's our faults. Let's not automatically rescale. Let's set the range. Let's go to 0 to 5. So now we're up at 5. So let's now rewind up here in the left arrow. And so now let's start stepping through. And if you'll see that the model is just deforming as we go forward in time. There, we're starting to, now we're getting, you can see the slip there. So I'll rewind it just a little bit. So our slip is starting right up in here. I can even zoom in. So now I've rescaled to this time step. So you can see our slip started right up here at the top of the faults. So we fast forward, the slip spreads, everything slips, and now it's going to lock back up again. And I didn't do the slip rate. Could have done the slip, could have output the slip rate. And so we need to rescale our slip again. So rescale range, go back to, let's say, 5. So here, let me play a little more of the movie. So, oops. So it's stuck. There, so now you can start to see right up in this region, it's starting to nucleate again. Generate some slip. Slips a lot, and then locks back up again. So stick slip behavior with rate and state friction in a quasi-static simulation. Any questions on visualizing this result? Okay, so let's go back and make some mistakes. Oops. So let's go to the terminal, and I'm going to go over here in my editor, and behind the scenes I'm going to change something, and we'll see if we can figure out why things go wrong. Go back to my terminal. So now we're going to run step 14 again. And we'll watch the output. So it's hard to tell right now what's going on. So I'll just sort of, all I'm doing is watching what's being written to the log file. So I can stop this, and you'll see the simulation is still running there. And so I'm going to do a grep for nonlinear in my log file to see, get an idea of what's going on. One thing we'll notice, our nonlinear solve isn't taking one iteration, and we think it should be stuck. It's taking 17, 10, so our nonlinear solve is converging. Our linear solve is converging. Let's look for diverged. Nothing diverged. Nothing diverged. It's still running. Still running. Whoa, took 116 iterations. Going pretty slow. So we have a question on how to determine the appropriate time step. So if we look at our velocity boundary conditions, they're going at a constant velocity, so we don't really get any hint of time step information from that. So the only other place so if we had I believe, so we didn't change what our material looks like. So we have an elastic material in the lower crust and upper crust. So we have no time step or time, variation there. So then that leaves the only time dependence we have in the problem in terms of sort of a scale is the fault behavior. And so rate and state friction. So we chose a coefficient of friction, we chose A and B parameters, and we chose the value for L, which is it's still running, and we chose L, which is also known as D sub C. And so that actually gives us what our time dependence is. So how fast the fault reacts to sort of the stick-slip behavior, because there is this transition from sort of, you'll notice we didn't resolve in fine scale that nucleation. It did occur over several time steps. Then the slip occurred over a few time steps. Then sort of, if we had a much finer scale sort of spatial resolution, then I probably would want to actually see that nucleation develop instead of just over sort of one cell. I'd want to see it develop over, say, 5 or 6, maybe even 10 cells in terms of diameter. So that would give me my spatial and temporal resolution. I don't want to see it develop over multiple time steps. So you can tell by how, if you're interested in really, how much the fault slipped and how fast it slipped, and really sort of capturing that decrease in the coefficient of friction through the sliding behavior and then locking up again, then you would want to use a finer temporal resolution and smaller time steps. So let's see if this is still going. So it's done. Let's see. So it actually converged. And so this is going to be pretty interesting to look at the results. So let's look at the ground surface first. Oh, we can run them both in. So ground surface scale by 200, I believe. So right there, first time step, we're getting slip. That doesn't look right. Faults, we get slip. Let's scale it. So we get 1 meter of slip. It's occurring in a corner. Let's see sort of play. So let's rewind that. So here we're getting slips of 0. We had slips of 1. So you can pretty much tell from this, even though we converged, we're basically getting garbage. Oh, you can't. Oops.
Yeah, it's just blue.
I was still probably sharing the terminal. Okay, now that looks better. So here's the garbage we're seeing. So first time step, I have a meter of slip up here in the corner. I have slips of 0, Second time step, I have slips between 0 and 0.3. So you can see my slips are just sort of oscillating around values. They're not coherent in terms of, you see them. It looks like I'm basically looking at numerical noise. So I converged, but I was getting numerical noise. And so what that's telling me is that, for one, I got slip at that first time step when I didn't expect slip. So that must mean that my stick-slip behavior is not occurring correctly. So if we go back now, exit, I'll remember to stop sharing. And I'll go back to the terminal here. And so I'll load up. And so you notice what I did is, here's my absolute tolerance. Well, my absolute tolerance from a linear solver is 10 to the minus 9. So it's bigger than my friction tolerance. So I better push it down to, let's say, back to 10 to the minus 12. So that's absolute tolerance 10 to the minus 7. Let's see what happens if I keep it at a pretty big value. Looks like we're trucking right along. So now we're back to, we're getting stick behavior, we're getting the fault locked. I can see that because we didn't need any nonlinear iterations. The one, we had our stick slip events. Notice that now with our greater tolerance for the nonlinear solver, we only took about 20 iterations. Rather than, I think, before up until the 30 to 40 iterations. And we see we're done, so our nonlinear solver converged. Let's look at our linear solver converged. Looks like it did. We'll do a grep for diverged, nothing diverged. So we look good. So in this case, we don't see a problem with our, we seem to have solved the problem as before. And so let's look at the output. I'm going to try and see if I can get away without reloading. Yes. So in VTK files, because the files changed, ParaView did recognize that, and I didn't have to delete them. So here's our ground surface. I want to make it wireframe again. So here's the absolute tolerance values depend on the dimension of the domain and the nature of the problem. They don't depend on the dimension of the domain, really. You'll notice that because we non-dimensionalize our everything internally within Pilot, the solver tolerances are operating on the non-dimensionalized values. So if you've non-dimensionalized things reasonably and consistently, then you don't need to change your solver tolerances. If you do start changing your your sort of spatial resolution or discretization size, then you may need to adjust your solver tolerances. Also, if you're trying to capture very slow slip, and, if you're operating your time scale is years and you're trying to resolve slip rates of 10 to the minus 13, then you are going to have to use very small solver tolerances. But in general, it's not going to. Generally, if you non-dimensionalize things correctly, you shouldn't have to play around with the order of magnitude of your solver tolerances. unless you're really switching from something that's fast deformation versus slow deformation. So let's play the movie. It doesn't. So I'm seeing stick slip behavior. So it looks like, using an absolute solver nonlinear tolerance, we're able to get away with a much larger absolute solver tolerance than what we had in the beginning. So we had to make sure that our linear solver tolerance was smaller than our zero tolerance associated with catching the stick slip. Any other questions? Charles, have we answered all of those that have appeared?
I think so.
Okay, then any questions on these quasi-static problems before we look at a couple dynamic problems? Actually watch some seismic waves move through our domain. Okay. So let's go back. And so now we're going to switch. I think I need to go back to